Okay, welcome to Mech Zone. Till the last lecture, we have studied about the basics about conduction, convection, and radiation, and we also studied in depth about the topic of conduction in case of slabs, in case of cylindrical wires, and in case of spherical systems. Now, today we will be discussing a very important topic, that is critical radius of insulation. Critical radius of insulation is generally asked almost every year for about 1 or 2 marks, and it is a guaranteed question in GATE, and this time in 2018 also we are expecting this 1 mark question or 2 marks question for sure. Now, to start with, what is actually an insulation? If we talk about an insulation, is generally a material which has the tendency to alter the heat transfer process. Now, alter heat transfer process can have 2 possibilities, that is either to increase the heat transfer rate or to decrease the heat transfer rate. So an insulation can be used either to increase or decrease the heat transfer rate. Insulation materials generally that we have discussed in the previous lectures, they were asbestos, then we had wool, then we have air, and etc. These were some of the common insulating materials that have been discussed in the previous lectures. Now, for example, if we consider a wire such that the diameter of the wire is very less, then this wire becomes actually very thin wire. So in case of thin wire, and if this wire is carrying certain amount of heat, then it becomes very necessary to remove this heat which is being generated in the wire. Now this heat can be effectively removed by means of an insulation that is placed around the wire. So by placing an insulation around this very thin wire, the heat transfer rate can be increased. Now, if we take the example of a wire such that this wire is very thin and it has an internal radius of Ri, and such that it is covered by means of an insulation externally, this shaded portion represents the insulation which has been added to this wire externally, such that the thermal conductivity of this insulation is K, and we know that thermal conductivity of this insulation is going to be very small because it does not generally conduct heat. But here in this case, in case of critical radius of insulation, the case may be something else. Now, the external radius after adding this insulation is R0. The temperature of the ambient surrounding or the atmosphere is T infinity, and the temperature of the inside surface of the pipe is Ti. Now, this is a cylindrical system, and now if we wish to draw the circuit diagram for resistance and heat transfer, then we will have this is temperature Ti, this is temperature T infinity. Between Ti and T infinity we have thermal conduction resistance for cylinder, that will be ln R0 upon Ri whole upon 2 pi KL, where L is the length of the cylinder. And this between Ti and T infinity, what we have the convection heat transfer resistance, and that will be 1 upon H into area. Area will be 2 pi R0 L. This is the resistance between Ti and T infinity. This is the resistance between Ti and T. I will write as T outside. Okay, this is Ti, this is TO, and this is T infinity. Very simple. Now, if I wish to write down the equation for heat transfer, that will be Q equals Ti minus T infinity whole upon ln R0 over Ri upon 2 pi KL plus 1 upon H 2 pi R0 L. Okay, now in order to find out the critical value of this outside radius, that what should be the value of this outside radius in order to alter the heat transfer rate, whether to maximize it or to minimize it. Now, to apply the condition of maxima and minima, what we will have dq upon dr naught equals to 0. Now on differentiating this equation with respect to R naught, we will obtain R naught equals K upon H. R naught equals K upon H, where this R naught is called as the critical radius of insulation. This is called as the critical radius of insulation. K is the thermal conductivity of the insulation that is being added. Please mind that it is the K of insulation which is added. K of the insulation. H is what? It is the convective heat transfer coefficient of the ambient. This is of the ambient surrounding. This is of the ambient surrounding. Okay, so R naught represents the critical radius, K is the thermal conductivity of the insulation, and H is the convective heat transfer coefficient of the ambient surrounding. This formula has been obtained by treating all other parameters to be constant. Okay, and H is also considered to be constant here. Now let us talk about what is the actual physical significance of this critical radius of insulation. For example, if I draw a graph between radius and heat transfer, what we will observe? We will observe that the heat transfer rate first increases, reaches a maxima and then decreases. It reaches a maxima and then it decreases. So actually this point where it becomes maximum is R naught, that is at critical radius of insulation the heat transfer is maximized, that is Q is maximum. And after that, if after the value of the critical radius we keep on adding the insulation, then instead of increasing the heat transfer rate, it will definitely decrease. It will definitely decrease. Please note that this graph is very, very important because this can be directly asked in 1 marks question, that explain or what will you say about the variation of heat transfer with respect to radius. So it first increases, becomes maximum and then decreases. The value at which the heat transfer rate is maximum is called as the critical radius of insulation. Now up to the critical radius of insulation there is an increase in the heat transfer rate, that is if this wire is carrying heat. If this wire is carrying heat inside, for example this is an electrical cable, so heat is being generated according to the I square RT, that is the Joule's law of heating. Now this heat also has to be removed. So if up to the critical radius we are adding this insulation, then the heat transfer will definitely increase. Now after reaching the critical radius, if we still keep on add the insulation around this wire, then instead of increasing the heat transfer rate, there will be a decrease in the heat transfer rate. So logically we can say that after this point the heat transfer will definitely decrease and this insulation will be of no physical significance. So actual significance of critical radius of insulation is up to the R naught point where the heat transfer is being maximized. Now what leads to this increase in the heat transfer rate? What actually leads to the increase in the heat transfer rate up to the R naught point? Now this is a point which is to be noted. It is an important point, very, very important, I must say, star point. Now what happens is when we add the insulation, there are mainly two resistances. One is the convection resistance, other is the conduction resistance. Now on adding the insulation, this convection resistance drastically decreases. It decreases drastically, whereas in case of conduction there is a very little bit increase in the conduction resistance. So overall speaking, the R overall decreases rapidly. R overall decreases. So when the R overall decreases, R overall is the overall resistance which is being encountered by this heat flow. So when it is decreasing, then definitely Q will increase, and that is why we have an increase in the heat transfer rate up to the critical radius. Okay, this is the reason why the heat transfer is increasing, because the convection resistance is drastically decreasing and conduction resistance is increasing a very little bit. Okay, it is increasing a very little bit. and therefore there is an increase in the overall decrease in the overall resistance, and as a result of which the heat transfer is increased. So this was the case up to the critical radius of insulation. Now what happens when we add the insulation even after the critical radius? Now here I will write after adding insulation beyond R0. Now if on reaching R0 we still keep on add the insulation, now what will happen? Now this is a very important thing which is to be noted here, that now instead of increasing the heat transfer rate, the heat transfer is decreasing. The reason is why? Because the convection resistance on the convection resistance is being decreasing a little bit. This will decrease a little bit, and conduction resistance increases rapidly. It increases rapidly. That means the reverse is happening in this case as compared to the previous one. The convection resistance is decreasing rapidly in the previous case, and the conduction resistance is increasing a little bit. Whereas after adding the insulation beyond R0, convection resistance little bit decreases and conduction resistance increases rapidly. So we can say that R overall actually increases. R overall increases rapidly, and hence Q will definitely decrease. So this is the reason why heat transfer after R0 is rapidly decreasing. Now if we talk about the practical applications of R0, that is the critical radius of insulation. Now this is a very simple topic. Okay, now for example, we have an electrical cable such that it is carrying electrical current. It is carrying electrical current. Internal radius Ri, external radius R0. This shaded portion represents the insulation which is being added here. Okay, and such that the thermal conductivity of this insulation is K. H is the ambient convective heat transfer coefficient. Now we know that when this wire is carrying a current, say I, having a resistance R, then according to the Joule's law of heating we have I square RT. Okay, this will be the amount of heat which is being generated in the wire. This amount of heat is being generated in the wire. Now according to the Joule's law, this heat is generated. Now this heat also needs to be removed, so this heat will be convected off to the ambient. Okay, this heat will be convected off to the ambient. So the rate of this heat loss can be increased by adding the effective insulation around this wire. Now you mind that this insulation should be added only up to its critical radius value, because in the previous graph we have observed that heat transfer rate definitely increases up to R0, and after which it decreases. So we will add the insulation up to the critical radius point, okay, so that in order to enhance the heat transfer rate. Now one very important observation in this phenomena, that is if the temperature of the wire is increased. If the temperature of the wire is increased, then we know that when the temperature is increased, the resistance will also increase. And when the resistance will increase, according to this phenomena, according to this formula, heat in the wire will be increased. Heat generation will be increased. And when the heat is increased, there will be more loss of power. Okay, so the temperature in the wire should not reach beyond a certain value, because it may even lead to the melting of the wire or burning of the wire. Now if we talk about the critical radius of insulation in case of spherical systems, previously we discussed about cylindrical systems, now we will be discussing about the spherical system, such that this is actually the insulation that is being wrapped around the inside sphere, such that the inner radii is R1, outer radii is R0. Now if we write the equation of heat transfer for this case and then differentiate it with respect to R0, we will observe that R0 here is equals to 2k upon H. R0 here will be equals to 2k upon H. So if we compare it with the previous formula, it is 2 times the previous formula, that is R0 is equals to 2k upon H. K is the thermal conductivity of the insulation which is being wrapped around it, and H is the convective heat transfer coefficient of the ambient. H is the convective heat transfer coefficient of the ambient, and if any of the value is being asked, then we will simply put it and get the answer. Now next topic that we will study is conduction through a sphere. Now we know that a sphere has 2 radii, R1 and R2. R1 is the inner radii, R2 is the outer radii. Okay, now if we recall our Fourier's law of conduction, that is Q is equals to minus Ka dt over dr. There we had X, but now since there will be the radial conduction of heat through the sphere, we will write R. Okay, this is Q. So QR is equals to minus Ka dt over dr. This is actually the equation of heat transfer in case of conduction through a sphere. Now what we will do, what will be the area in case of the sphere? The area in case of the sphere will be 4 pi r square. So instead of r square we will write r1 r2. We will write r1 r2. So this is the area which is being encountered at any normal direction during the heat flow. So Q is equals to minus K 4 pi r square, we will write here, say dt over dr. Now Q dr upon r square is equals to minus 4 pi k dt. Now solving this equation and putting the limits R1, R2, T1, T2, inside temperature is T1, say inside temperature is T1, outside temperature is T2, this radius is R1, this radius is R2. Okay, now so what we will get, after solving this equation, we will obtain that Q equals to 4 pi k R1 R2 T1 minus T2 upon R2 minus R1. We will obtain this formula for heat transfer. Now if we compare this formula with the conduction in case of slab, then we will obtain that resistance, our thermal resistance in case of spherical system, that will be equal to R2 minus R1 upon 4 pi k R1 R2, where K is the thermal conductivity of the material which is used to make this sphere. Okay, so R thermal conduction in case of sphere, conduction resistance in case of sphere is R2 minus R1 upon 4 pi k R1 R2, whereas in case of cylindrical resistance was equals to ln R2 upon R1 upon 2 pi k L. This was the resistance in case of cylindrical system, and this is the formula for resistance in case of the spherical systems. Now if the question is asked what is the type of variation in temperature, temperature variation. Now in case of the slab, the variation in temperature was linear. In case of cylindrical system, the variation in temperature that was observed was logarithmic variation of temperature in case of cylindrical, and variation of temperature in case of sphere is hyperbolic variation of temperature in case of spheres, whereas logarithmic variation in case of cylinder and linear variation in case of slab. Up till now we have been studying about the generation of heat in case of steady systems, but now we will see for unsteady systems also. So we will now study the unsteady heat generation cases. Unsteady heat generation. Unsteady simply means it does not remain constant with time. It is changing with respect to time, such that the heat generation changes with respect to time. Now, the equation, that is, we will have a time varying temperature gradient, dt upon d tau. dt upon d tau is when the temperature is changing with respect to time. Now, there are certain equations. I am not deriving all those equations because that is not very important. What is important is just to know those equations. That is, if we write the heat conduction equation in the 3 dimension, that will be del square T upon del x square plus del square T upon del y square plus del square T upon del z square equals to plus q upon k is equals to 1 upon alpha dt over d tau. 1 upon alpha dt over d tau. Okay, so this is the equation of heat conduction in case of 3 dimensions, because we are considering x, y and z, all the 3 coordinates. Q is the amount of heat which is being internally generated in the system. K is the thermal conductivity. Alpha is known as the thermal diffusivity. It is known as the thermal diffusivity. It is known as the thermal diffusivity of the material. Thermal diffusivity is actually again a thermophysical property, and alpha is equals to K upon rho Cp. K upon rho Cp, where K is the thermal conductivity, rho is the density of the body, and Cp is the specific heat. Okay, now if we talk about Poisson's equation, it will be nabla square T plus Q upon K equals 0. This is the Poisson's equation. This is the Poisson's equation. That is, this is equals to 0 means this part is 0. That means there is no change of temperature with time. Okay, now if, and Q is the amount of heat which is being internally generated. Now if we take Q equals to 0, that means if we assume that no heat is being generated in the system, then nabla square T equals to 0. This is the Laplace equation. This is the Laplace equation. So if we discuss about alpha, alpha is the property which tells us about how fast the heat is being diffused into some material. It also tells us about the ability of the material to diffuse the heat energy more rapidly. So if we compare between alpha of the gases and alpha of the liquid, then definitely we will find out the ability of the gases will be much more as compared to that of the liquids. Okay, and one more thing, higher the value of K, higher the value of alpha. Lower the value of Cp, higher the value of alpha. Lower the density we do not talk about. We generally talk about Cp and K. That is, higher the value of K. So compare a substance having very high value of K will show very low value of Cp, and eventually alpha of the body will be very, very large. Okay, alpha of the body will be very, very large. The equation that we have written, this equation, this is called as the generalized equation. This is called as the generalized equation. This is called as generalized equation. Now in the generalized equation, if this Q is equals to 0 and dt upon d tau is equals to 0, then we will have del square T upon del x square plus del square T upon del y square plus del square T upon del z square equals to 0. This will be 0 only when there is no internally heat generated and the temperature is not changing with respect to time. So this is again the generalized equation, and this is nothing but nabla square T equals to 0 that I have written. That is the Laplacian equation. Okay, now we will study about the heat generation in case of a slab. Earlier there was no concept of heat being generated inside a slab. Okay, now we will see that heat is being generated inside a slab and it is being convected off to the ambient from the walls. These are the walls of the slab, such that this wall coordinate is x is equals to minus L. The middle of this slab would be x is equals to 0, and to the extreme right we have x is equals to plus L. So total length would be 2L. Okay, so total length of the slab is 2L, such that the extreme left is on x is equals to minus L, middle is x is equals to 0, and extreme right is x is equals to L. Now, to maintain the steady condition of the slab while the heat is being generated, which is so the heat must be convected off from both the walls to the atmosphere. Then only the steady state in this slab will be maintained. Okay, steady state. Now for steady state we have del T upon del tau equals to 0. Okay, then we will have del square T upon del x square. I am considering the heat conduction only along the x direction. I am considering only along the x direction. Along the y and along the z it is 0, plus Q upon K equals to 0. So Q is the amount of heat generated, K is the thermal conductivity of this slab material. Then we have del square T upon del x square equals to minus Q upon K. Now if we write del square T equals minus Q del x square upon K, okay, just we have simply del x square, we have simply multiplied this del x square on this side.